Hey everyone, it's Mrs. Brimlow, and today we're going to go over the real number system, our unit from earlier in the year. So make sure you have your RICAS review packet so you can copy down the examples as we go. So in this unit, there were a few major ideas that we learned. We learned about the real number system and the difference between rational and irrational numbers. We also talked about square roots and cube roots, and we talked about writing repeating decimals as fractions. So we're going to go through some examples of all of those ideas in today's review. So starting with the real number system, the main difference between the two major categories, rational and irrational, is that rational numbers can be written as fractions. Irrational numbers cannot. Within the rational numbers category, we have several smaller categories, starting with natural numbers. So natural numbers, if you think back to when you first started learning numbers, or someone would say, go ahead and count 1, 2, 3, 4, so on and so forth. So they're positive whole numbers. Then we move into our whole numbers category, which contains all of the natural numbers, but we add the number 0. Then we move into integers, which includes all of our positive whole numbers, and now it includes their opposites or negative numbers, but they're still whole numbers. Sorry, my cat came to visit. You need to go. So -1, -2, so on and so forth. And then we get to the overarching category, which is rational numbers, and that includes fractions as well as decimals. When they're decimals, that means they're going to repeat the same pattern forever, or they're going to terminate, which means to end. So we have a couple examples of fractions. This is a repeating decimal. Notice it has a bar over the numbers that says it's going to repeat. And then we have decimals that terminate, which means to end. So this decimal ends after the 5. Now, we also talked this year about square roots, which we'll talk a little bit more in depth in a minute, but the types of square roots or cube roots that would fit in the rational category would have integer answer, sorry. So square root of 1 is 1, square root of 4 is 2, so they come out to either a positive or negative whole number. If they come out to anything else, it will be a crazy decimal, which we would put in the irrational number category. So irrational numbers cannot be written as fractions. In decimal form, they go on forever and there's no clear pattern. The numbers could repeat within the decimal, but there isn't a clear pattern to show that it's rational. So our two most famous numbers we see are the square root of 2, and they show us the beginning of that decimal. Notice the 3 dots at the end. That tells us it's going to keep going on forever, but because there's no clear pattern in front of it, that tells us it's irrational, and then we have pi. Now, regardless of if the number is rational or irrational, they would be considered a real number, the entire category, that purple box. And all of these numbers together can be written on a number line. So we're going to dive into square roots first. So perfect square and perfect cube. So perfect square is based on the shape of a square and how you'd find the area side by side. And we know for squares, it's a number times itself. So 1 squared means 1 times 1, which gives you a product of 1. So 1 is a perfect square. 2 squared means 2 times 2, which is a product of 4. So 4 is a perfect square. So all of these positive or negative numbers that you multiply by itself, their product is a perfect square. And the reason I said negative as well is because, I'm just going to do this off to the side. If you have -3 squared, notice that it's in parentheses. This is saying -3 times -3. By rules of integers, a negative times a negative is a positive, and then the final answer would be 9 because 3 times 3 is 9. So you can use negative numbers. However, if it looked, I'm going to just put it right above, if it looked like this, what this is saying is different. This is saying -1 out front times 3 times 3, and that would give you -9. This is not a perfect square because now we have that -1. It has to be a number times itself. So if it's in parentheses like this, so -3 times -3, that works. The top one does not. So just be mindful of how numbers are written. Okay? And that's important for when we talk about square roots. And then perfect cubes is like a cube. So if you think of like a dice, it's a 3D figure, and it means volume. So a number times itself 3 times. Now with cubes, they're a little bit different. You can have a negative answer because, I'm just going to do it right here. If I do -2 times -2 times -2, a negative times a negative is a positive, times another negative would make my final answer negative. So cubes, you can have negative answers, and when you're taking cube roots, they can be negative, but that is not the case when you're talking about square roots. So when we're talking about cube roots and square roots, the square root of number is asking yourself what number times itself gives you that as a product. So the square root of 1 is 1 because 1 times 1 is 1. Square root of 4 is 2 because 2 times 2 is 4. Square root of 9 is 3 because 3 times 3 is 9, so on and so forth. Now, square roots can be negative. I should say they can have a negative answer. So for example, if I was asked to take the square root of 9, it could be 3 because 3 times 3 is 9, but it also could be -3 because -3 times -3 is 9. Okay, it's the same number times itself. What we can't do is take the square root of a negative number. There is no number times itself that would give you a negative answer. The only way to get -9 would be to do a positive times a negative. Those are not the same numbers. So this is not possible. And you'll actually learn more about this later on, I believe in Algebra 2. But for our purposes right now, it's not possible in the real number system. So square roots, when you take them, as long as it's a positive number underneath, you can solve that to be positive and negative, but you cannot take the square root of a negative number. Now it is different for cubes, because once again, we're working with 3 numbers. So if I want to take the cube root, let's say, of -8, we'll just see, because you can see the example at the top, this would just be -2, because that's the only way you can multiply to get an answer of -8. I could also take the cube root of just 8, and that would just be +2. So make sure you copy this down so you have these examples to refer to. So in order to estimate a square root when we don't have a calculator, and these questions on RICAS, 95% of them, you will not be able to use a calculator, you need to know your perfect squares. Usually they don't go up much higher than 144, so if you know your facts up to that point, you should be fine. It will definitely help you. So when we're trying to estimate a square root, that means that that square root is not going to be a rational number. It's irrational. It's a long, long decimal, so we estimate. So when I'm trying to find it, what I do is find the 2 consecutive perfect squares around that number. So for example, for 34, I have 25 and 36. So the 2 consecutive perfect squares around 34. The square root of 25 is 5, and the square root of 36 is 6. Therefore, the square root of 34 is somewhere between these 2 numbers. Okay? Now, it's an estimate, so we have to kind of guess what the decimal would be and where this would be on the number line. So I come back here to this step to see how far away is 34 from these numbers on a number line. So this has a difference of 9, and this has a difference of 2. So that means 34 is a lot closer to 36. Therefore, the square root has to be closer to 6, but not bigger. So they estimated to be about 5.8. You could also say 5.9. Remember, it's an estimate. It needs to be reasonable, but it's an estimate. So there could be several different answers. Now, if you said 5.1 or 5.2, that wouldn't be a reasonable estimate. 34 is closer to 36, so it has to be closer in terms of its square root on the number line. So we're going to do this with the square root of 58. So the 2 consecutive perfect squares around 58 are 49 and 64. The square root of 49 is 7. The square root of 64 is 8. So that means the square root of 58 is somewhere between these 2 numbers. So coming back to these 3 numbers, to get from 49 to 58 on a number line would have a difference of 9, and 58 to 64 has a difference of 6. So it's a little bit closer to 64, but not a lot. So a couple of estimates you might have are 7.6 or 7.7. I wouldn't go much higher than that or lower, but these two would be reasonable. Okay. All right, so now we're going to move on to writing repeating decimals as fractions. So we've been writing decimals as fractions, fractions as decimals for a long time, but what we haven't done is repeating decimals as fractions. So just taking a step back here, let's say I had the decimal 0.5. So when we see a decimal, we read it as we write it. So I would read this as 5/10 because the 5, which is the last digit, is in the tenths place. If I had 0.37, I could read this as 37 hundredths because the decimal ends in the hundredths place. With repeating decimals, they don't end, so we don't know how to write them as a fraction because we can't read them with an ending place value. So we're going to do this algebraically because repeating decimals can be written as fractions. They're rational numbers. So we're going to let x equal this original decimal. Okay. Now, when we write fractions, we don't typically put decimals in our fractions. So I need to get rid of the decimal. In order to do that, I need to get one set of the repeating digits in front of the decimal. So the only digit repeating here is 7. So I want to move the decimal so I have 1 7 in front. So I want to move it this way so it's between these 7s. Whenever you're moving decimals, you need to multiply or divide by base 10. So 10, 100, 1,000, so on and so forth. Because we're getting bigger, we're multiplying. Because we're moving the decimal once, we're multiplying by 10. So I multiply by 10 on both sides to keep my equation balanced. So I'm getting closer, but I still have a decimal. I still have numbers after the decimal point, I should say. So to get rid of them, I'm going to subtract. So I'm going to subtract my original equation of x equals from my new one that I just multiplied. So this allows me to subtract. Even though these decimals are going on forever, they're the exact same decimal. So they would cancel out. So 7 minus 0 is 7. And then 10x, this is really like a 1x. So when I subtract those, I'm left with 9x. Now, solving equations tells me if I divide by 9 on both sides, I would get x equals 7/9. So we're going to try this now with this decimal 0.39 repeating. So we're first going to say let x equal. Now, in this number, I have 2 digits repeating. Therefore, I have to move the decimal 2 times. So I need to multiply this time by 100. So it's going to look like 100x equals 39.39 repeating. So I have one set of the repeating digits now in front of the decimal. So to get rid of the decimal, I'm going to subtract the original. So those will cancel out, leaving me with 39 on this side. And on this side, I'm left with 99x. So to turn this into a fraction, I'm going to divide by 99 on both sides. So x equals 39 over 99, which I can simplify to be 13 over 33 because both numbers are divisible by 3. Okay? When you can simplify, you should. Now you might be noticing a pattern. So for 0.7, we had 7/9. For 0.39 repeating, we had 39 over 99 originally before we simplified. So the general pattern for basic repeating decimals like this is however many number of digits are repeating, that's the number of 9s you will originally have in your fraction before you simplify. I only have 1 digit repeating, so it's 7 over 9. This one I have 2 digits repeating, so it's going to be 39 over 99. So if I had 0.135 repeating, this would be 135 over 999. Of course, you would want to simplify if you could. And I want to point out that this pattern only works when all digits are repeating. If you had something like 7.35 where only the 5 repeats, this wouldn't work. You'd want to use the algebraic way to write this as a fraction because it is possible. So this trick only works when all digits repeat after the decimal. So this review, it should cover everything you're going to see on RICAS and in your practice.